where we left yesterday. I am audible, right? My voice is clear. No signal disturbance, I guess, right?
No, sir, it's clear, sir.
Okay, thank you. Okay, so what I will do today is I will continue with where we left yesterday. Of course, I started my lecture yesterday with the Nobel Prize, of course, introducing the institute. And then I started my lecture with the Nobel Prize. So you guys would have read today's newspaper that yesterday Nobel Prize in Medicine was announced, correct? That is to the discovery of hepatitis C virus, right? So keep watching this Nobel Prize website even for today and throughout this week. So every year during the second week of October, the Nobel Prizes, the Nobel Prize winners will be announced. And on December 10th or 11th, the award ceremony will happen, as I mentioned yesterday. Okay, so we went on yesterday and discussed about the fundamental concepts in electrochemistry, some of the basic principles, theory behind origin of potential, current, etc. Then I started with the technique, right? So what I will do today is, of course, today also I will start my lecture with slightly a different story that why one has to worry about doing research. And slowly I will continue with techniques and I will talk about electrocatalysis. Okay. Now, so why do you think people are involved in doing research? It's not like there are no other options to get a job. So people got job like scientists, lecturer, academicians, etc. And simply for the sake of doing something, they do research, right? And they do publish papers just to get their promotion, etc. It's not the case, okay? So research is a kind of passion, and people are involved in doing research to sort out global issues and to provide viable solutions to our society. For example, in this slide, you can see I have listed down the humanity's top 10 problems which we will face in the upcoming 50 years or so. Okay, so these are the top 10 problems we will face in the upcoming 50 years. As you can see, the list starts with energy, water, food, environment, poverty, terrorism, disease, education, democracy, population, etc. As you can see, energy is the first and foremost priority. I can give examples for each of these. Okay. For example, about 2 decades ago, maybe around 1990s, maybe 2-3 decades ago, we do not had mobile phones, right? I remember when I was doing PhD at Bangalore, I used to go to STD booth and call my parents and talk over telephone. But now you have the whole world, and the world of information is at your palm, right? So mobile phone has revolutionized the way we communicate. And also we moved from classical blackboard based teaching to a virtual platform. Now we do have online classes. So all these things happen because of the revolution in the field of energy sector as a whole. Okay, so imagine about I remember it was about 4 or 5 years ago in Tamil Nadu. I think we had 14 to 15 hours of power cut. Remember we have 24 hours a day, and out of which 14-15 hours of power cut we had. So energy is going to be a very, very critical issue. Apart from this, you can name any house in the village now. There are no houses without the following 3 items. 1, mobile phone. Second, two-wheeler. And third would be like, television, etc. So if you don't have power, how are you going to cope up with the energy? Which is a very, very critical question. When I say energy, it's not just about energy storage devices like battery or supercapacitors alone. It also deals with fuel cells, the mode of transport, those kind of things also comes into picture. Now, like this, of course, I can give examples for each of the topic here. For example, disease. Let's say when we were kids, about when we were kids again 2-3 decades ago, we don't had many diseases like, chikungunya, Nipah virus, now even COVID-19, etc. We had probably fever, a high fever like pneumonia, jaundice. Those are the things those diseases commonly prevail in the society. But now, if you go to a doctor, with a headache, what are the questions one would face? Again, keep it in mind, it is not to criticize anyone. It is to understand how we are progressing in the field of science and technology. Okay. So if you go to a doctor, the first question he would ask is, sir, did you check your blood pressure level? Did you check the glucose level in your blood? Why don't you take an ECG and check whether your heartbeat is functioning properly? Remember, you would have gone just to have a tablet for a headache. So that's the kind of state we are in. So how do you provide solution to these global issues? The only way to provide a solution to these global issues is through science and technology. Okay. Apart from this, 2012 human population across the globe was estimated to be 6 billion, and it is expected to grow roughly twice by the year 2050. Okay. So how are you going to provide them, clean drinking water, good energy backup for digitalized India, and good food for us to live, So all these things is a giant question mark. And the only way to provide a solution to this is through science and technology. And if we do such kind of thing, we can go inch towards closer step towards self-reliant India. What our Honorable Prime Minister's vision is Atmanirbhar Bharat. So we can become self-reliant in all this field, and the dream of self-reliant India could be realized. Okay. So now these are the hot two topics right now in the field of research in general. One is an energy crisis, and the other one is a healthcare diagnostics. Okay. So what do I mean by energy crisis? Probably people would have talked about this. A lot of people even don't know what do they mean by energy crisis. So it's a kind of we need to create transparency about energy crisis. Okay. And we need to eradicate this energy illiteracy. As far as the science is concerned, we need to come up with a balance sheet, meaning what are the sources available with us to produce energy, and how do you basically store and convert energy into useful form. Okay. I don't want to touch upon the healthcare diagnostics as of today, because that's not the primary aim of this faculty development program, neither my lecture. But the point I want to stress here is only through science and technology you can provide solution to all this problem. Right. Now, maybe for a minute or two, let's recollect what we discussed in the field of fundamental electrochemical concepts yesterday. The potential originates in electrochemistry because of the spontaneous formation of double layer at interface. I can go even one step and say that electrochemical science and technology can provide solution to all this problem, especially in the field of energy. Okay, so that's where the potential originates in electrochemistry, and you can measure the potential difference by using a reference electrode. And the current comes from three different modes of mass transfer, like migration, convection, and diffusion. Remember, we need to eliminate the current contribution from migration and convection, so that the measured current would be purely of diffusion in nature, right? And we discussed about fixed laws of diffusion, and we discussed about potentiometry and amperometry. So in the series of techniques, why the electrochemical techniques are useful is because electrochemistry offers tool to understand the system at equilibrium, at steady state, and near to equilibrium and far away from equilibrium, so that one can arrive at a complete picture, complete processes involved in any kind of electron transfer reaction using all these techniques. Okay. So among the electrochemical techniques, voltammetry technique is the most popular and widely used technique in electrochemistry. In case of voltammetry, we do have linear sieve voltammetry, cyclic voltammetry, AC voltammetry, etc. Voltammetry is a process Okay, voltammetry is a process in which you apply a potential and measure current. Voltammogram is an output, is a plot between current versus voltage. Okay, so that's the hardcore definition of what voltammetry and voltammogram is all about. I repeat again, voltammetry is a process in which you apply a potential and measure the current. On the other hand, voltammogram is an output, is a plot between current versus applied voltage. Okay. So in case of voltammetry, we do have two different techniques like linear sweep voltammetry and cyclic voltammetry. What do we do in this technique is you sweep the potential of working electrode between two predefined limits. Let's say in case of linear sweep voltammetry, you linearly sweep the voltage between two predefined limits. Let's say between E1 and E2. Okay, you can vary between 0 and 0.5 volt versus the reference electrode. Remember, always a good electrochemist will say with respect to what potential you with respect to what reference electrode you apply the potential. Okay, so in case of linear sweep voltammetry, you linearly sweep the voltage between fixed predefined limits of the potential with respect to time. This is a kind of input signal, and the output would be for this voltage perturbation how the current varies with respect to the applied voltage. Okay, so that's the kind of output in linear sweep voltammetry. This is called a linear sweep voltammogram. For a given specific electron transfer reaction, let's say a species undergoes an electron transfer reaction, you would see typically a peak-shaped voltammogram as an output in voltammogram. Okay. The moment you see peak formation in such kind of voltammetry technique, that indicates 2 points. The first one, there is an electron transfer reaction. That's why you would see a peak-shaped voltammogram. And the second point is the process is controlled by diffusion. Okay, recall many different processes which occur in an electron transfer reaction. The probe molecule has to diffuse from the bulk to the interface, get absorbed on the electrode surface, undergoes electron transfer reaction to give you a product. The product has to desorb and diffuse back to the bulk of the solution. And I mentioned yesterday that among these processes, diffusion is the slowest, and that's the rate determining step. That's why the moment you see the peak-shaped voltammogram as an output in voltammetry, that indicates that there is an electron transfer reaction, and the second point is the reaction is controlled by diffusion. So diffusion is the rate limiting step. Now, maybe we can discuss about cyclic voltammetry. I can always correlate that with the linear sweep voltammetry. The half of cyclic voltammetry is called a linear sweep voltammetry. Okay. In fact, cyclic voltammetry is the most widely used technique in electrochemistry. Okay, it provides many valuable information and about the electrode-electrolyte interface in electrochemistry. In case of cyclic voltammetry, what do we do? If you look at the input perturbation signal, this is the input signal and that's the output signal. Okay, so the output is nothing but your cyclic voltammogram. Now, in case of cyclic voltammetry, you can change the voltage from again a fixed predefined limits. Let's say you start from an initial potential V1, you linearly sweep the voltage up to the other predefined limit, let's say V2, and on reaching V2, you reverse the scan direction. Okay, when you reverse the scan direction, you have options. You can come back either to same initial potential like V1, or even you can stop well ahead to another potential, let's say VA, or even you can extend beyond V1 to another potential value VB. Remember, all these techniques are also called as cyclic voltammetry. It is need not necessary that you need to come back to the same initial potential like V1 as a final potential. You can also go back to another potential. Okay, now the input perturbation signal, as if starting from V1 to V2 coming back to V1, comprises of one cycle in cyclic voltammetry. Similarly, if you keep on applying cycles like this, you are basically cycling the potential of a working electrode, and you are going to look at what's the output in case of cyclic voltammeter. Now, the rate at which you vary the potential with respect to time is called the scan rate, which is nu. Okay, the rate at which you vary the potential with respect to time is called the scan rate. Nu is equal to dou E by dou T, which is a very, very critical parameter. Okay, the scan rate is a very critical parameter in electrochemistry. Recall, yesterday I was talking about why we need to worry about electron transfer reaction. You know, we're taking good food, expressing our emotion, getting up and feeling hungry, you know, all these things happen because of the inbuilt redox reactions which occur in our body. Okay, now to understand the value of this scan rate, let's go back and look at, you guys should have heard about Jablonski diagram, right? In molecular spectroscopy, you guys should have heard about Jablonski diagram. That's where you distinguish the process of fluorescence and phosphorescence, right? How do we describe the Jablonski diagram? Suppose a molecule absorbs light in terms of radiation and excite from a singlet excited to, singlet ground state to singlet excited. Okay. When the molecule relaxes from singlet excited to singlet ground state, it emits radiation in terms of fluorescence. Rather than relaxing from a singlet excited, it can also relax from another excited state, which is triplet excited. When it relaxes from triplet excited to singlet ground state, and that process is called phosphorescence. You know, the time constant associated with such kind of processes are of the order of let's say nanoseconds to femtoseconds. Of course, it depends on the molecule, but in a broad range, you can provide a time constant in the range of nanoseconds to femtoseconds. Now, the electron transfer rate constant, the values of such electron transfer rate constants of the order of 10 power minus 15 per second, 10 power minus 18 per seconds are reported. So the electron transfer rate constants are such a fast reaction. Okay, so that's why the parameter scan rate becomes very critical. If you do not use the optimized scan rate, you may either miss the electron transfer reaction, or sometimes you may even overlook the electron transfer reaction. Do you get me? That's why the scan rate becomes very, very critical. So nu is equal to dou E by dou T or dE by dt, the rate of change of potential with respect to time, and the unit is volt per second. The recent addition being, even we have a fast scan voltammetry, especially to understand the electron transfer reactions associated with the protein biomolecule. We can use what is called fast scan voltammetry. Okay, now coming back to the discussion of cyclic voltammetry, the scan rate value is same for both forward and reverse reaction. Okay. Now, so you start from an initial potential V1, go to another potential V2 and come back to V1. This comprises of a single cycle, and that's the kind of input you give in the cyclic voltammetry. The typical output in cyclic voltammetry is a plot between current versus voltage is called a cyclic voltammogram. And suppose, let's say you want to monitor a redox reaction, you dip all the 3 electrodes into an electrolyte. You have a reference working and counter electrode, and in the electrolyte you have a redox probe like a ferrocyanide system, along with the supporting electrolytes like sodium chloride or sodium fluoride, etc. Okay. Let's say the moment you apply an initial potential, okay, normally they consider reduction as a standard reaction. Let's say, so the reduction could be ferrocyanide gains an electron, undergoes a reduction to give you a product ferrocyanide. Okay, reverse of this reaction. The moment you apply a potential, what happens initially is the molecules will be at a constant diffusion from the bulk to the interface. So initially there won't be any initially there won't be any current flow. Whatever the potential you apply would be contributed to double a charging effect. Okay, and at certain potential you see that the molecule started to undergo reduction. So that potential is called the onset potential for reduction process. So at this potential, whatever be the Fe3 plus ions come into contact with the electrode surface, gains electron from the electrode, undergoes reduction to give you product Fe2 plus. Okay, so this so the molecules of Fe3 plus at interface gets depleted, the concentration reduces, and in order to maintain the Nernstian equilibrium, more molecules of Fe3 plus will diffuse from the bulk to the interface. So this sets up a concentration gradient. Okay, recall Fick's first law. So according to this concentration gradient, there would be a current flow, and that is the current you measure in case of cyclic voltammetry. I hope you understand where the current comes from, right? So at onset potential, Fe3 plus undergoes a reduction, and the concentration of molecule at the interface decreases, and in order to maintain the Nernstian equilibrium, more amount of Fe3 plus will diffuse from the bulk to the interface. So this sets up a concentration gradient, and with respect to concentration gradient, there is a current flow in between working and counter electrode. Now remember, in cyclic voltammetry, you are keep on sweeping the potential. So the more and more you go to the negative regime, now we are going from 0.2 to minus 0.2. Okay, when you are going more towards negative regime, more and more reduction occur, the more and more concentration gradient set up, and that's why you get an increased current in cyclic voltammetry. And when you keep on scanning the potential further, you would observe that at certain potential, you reach the maximum current for the reduction process. So that is called the peak current for reduction. That is called IPC. At the corresponding potential, of course, is called peak potential for cathodic, meaning reduction process. Okay. The moment you cross the peak potential, there is a decrease in the current value. Okay. So at the peak potential, the rate of reduction is maximum, and the moment you cross the peak potential, there is a decrease in the current value. This is because although the reduction occurs even in this regime, the rate of the reaction is not maximum, the concentration gradient is not maximum, and that's why you end up with a reduction in the current, since the rate of reaction is not maximum. Do you get me? And that's why overall this behavior gives like a typical peak shaped voltammogram as an output in cyclic voltammetry. And the moment you keep on continuing the scan further, you would end up again in a regime where there is no electron transfer. So the regimes where there is no electron transfer reaction is called a non-Faradaic regime, and the regime where you have typical peak shaped voltammogram, the current contribution comes from both Faradaic and non-Faradaic. Predominantly the Faradaic would dominate in case of peak formed regime. Okay. I hope you guys follow what I am saying, right? Maybe too much of subject today, but it is okay. At least you can able to understand, right? I am audible, right? Or you guys simply switched off and went for listening to music? Yeah.
Yes, sir.
Yeah. Okay. Okay. Good. Because I want at least you guys to listen. I'm talking too much subject now. I do remember, but it is okay. Okay. Now, the same concept you can extrapolate to the reverse process as well. Okay. In case of typical redox reaction, in the case of forward scan, you monitor the reduction process, and on reaching this V2, meaning let's say about minus 0.2, you are going to reverse the scan direction. In case of reversing the scan direction, we will follow the oxidation process, meaning Fe2 plus loses an electron, undergoes oxidation to give you Fe3 plus. So similarly, the moment you start reversing the scan direction, initially there won't be any current flow. Whatever the potential you apply would contribute to double a charging effect. And at certain potential, you would see suddenly the oxidation current starts increasing. That is because Fe2 plus undergoes oxidation to give you Fe3 plus as a product. So the amount of molecules of Fe2 plus at interface decreases. In order to maintain again the Nernstian equilibrium, more amounts of molecule of Fe2 plus will diffuse from the bulk to the interface, and this sets up a concentration gradient. And the moment you keep on changing the potential further, the concentration gradient increases, in turn the oxidation current increases. Similarly, at certain specific potential, you would see the current for the oxidation process is maximum, and that current is called IP oxidation, and the corresponding potential you would observe a maximum current is called EP oxidation. And again, the moment you continue scanning the potential further, though there is an oxidation process in this regime, since the rate of oxidation is not maximum, the current decreases because the concentration gradient decreases. And when you keep on continuing the scan further, when you reach the initial potential like 0.2, you would end up with the regime again. There is no Faradaic process. It would completely reach the non-Faradaic regime. So this is the kind of typical output one would get in case of cyclic voltammetry. Now, the resultant peak current is related with many different parameters like number of electron transfer reaction, area of the electrode, concentration of the species, diffusion coefficient, and the scan rate through Randall-Sevig equation. This is a very, very useful equation in cyclic voltammetry. Okay. Here, as you can see, the peak current is directly proportional to square root of scan rate and directly proportional to square root of diffusion coefficient, and also directly proportional to number of electrons and concentration of the species. Okay. As you can see, this equation is like y is equal to mx form, you know what we studied probably in school, where if you plot y versus x, let's say IP versus nu power half, you would get a linear relation, you would get a linear plot that passes through origin. Maybe I will have that, yeah. So you would have a linear relation which passes through origin. Okay. So by looking at the slope and by using this Randall-Sevig equation, one can determine the number of electrons involved in the process if we know the diffusion coefficient, or if you know the number of electrons, you can determine the diffusion coefficient. Okay. So that's why this technique is a very, very powerful technique. Remember, when you keep on changing the scan rate, as you can see that the peak current increases both in forward as well as in reverse directions. Okay. Now, the formation of peaks in the forward and reverse scan alone is not a criteria to assess that the given process. The given process is a. Okay, I missed a slide. I think. Okay, it doesn't matter. Okay, the formation of peak both in the forward and the reverse scan alone is not a criteria to assess that the given electron transfer process is a single electron reversible process. There are 6 different diagnostic tests one has to follow. The first one is the peak-to-peak separation between the forward and reverse scan is about 60 millivolt, 59 by n millivolt. For a single electron, it is 59 millivolt. Okay, so that's the Nernstian relation. And similarly, there are 6 different diagnostic like peak current for both cathodic and anodic process should be same, and IP is directly proportional to nu power half, etc. You know, you guys can always read a book called Instrumental Methods of Analysis. Okay, Instrumental Methods of Analysis in electrochemistry. There is a book by Southampton group of people. A lead author is K.N. Bartlett. It is P.N. Bartlett. Okay, so that book is a good book to understand the techniques. Now, using cyclic voltammetry, one can assess reversible, irreversible, and quasi-reversible process. You can depends upon the electron transfer rate constant. You can see that for a typically fast electron transfer rate constant, you would get a very sharp peak in cyclic voltammetry. The moment you observe that the peak is drawn out, meaning a broad peak, the electron transfer rate constant decreases, and also the peak potential shifts in the positive regime. Okay, so these are some of the kind of information one can derive from cyclic voltammetry. Not just a reversible process, you can also assess irreversible process, and these are the diagnostic tests for irreversible. The complete irreversible process would display only peak in one direction. There is no reverse peak. Okay. Similarly, there are diagnostic tests one can follow, and also apart from reversible and irreversible, you can assess quasi-irreversible process by following this diagnostic test. Okay, so these are some of the valuable information one would get from cyclic voltammetry technique. The many different processes, what I explained for a general concept like diffusion, adsorption, etc. You can analyze electron transfer reaction, right, and diffusion using cyclic voltammetry. Apart from this, one can also analyze the adsorption process which occur in any kind of electron transfer reaction. In such case, okay, in case of adsorption, you would see that the peak to peak potential between forward and reverse scan is 0, meaning delta EP is 0. You will see peak formation both in forward and reverse direction at the same potential. By integrating the peak, you would get a value of charge. By measuring the charge, you can determine the surface coverage of molecule using this formula. Lambda is equal to Q by N of A. Okay, so that's the kind of advantages one can get. You can determine the surface excess, surface coverage, etc. by looking at the peak current and correlating with this phenomena. So not only that, you can also assess the cleanliness of the electrode surface. I'm sure whomever is doing PhD in the field of electrochemistry, they normally polish the electrode surface, and it is very difficult to get the reproducible result. I do understand, but how do you get the reproducible result? Only through polishing the electrode uniformly. And you can also polish not just by mechanical polishing, you can also do an electrochemical way of polishing. Using a cyclic voltammetry, you can run a CV in an acid medium like sulfuric acid, HCl, perchloric acid, nitric acid, etc. so that you would get a reproducible surface. The typical behavior to assess the cleanliness of platinum electrode is by observing this kind of peaks. Okay, so this suggests that if you do a cyclic voltammetry experiment in sulfuric acid, you would typically observe hydrogen adsorption and desorption peak on platinum electrode. By integrating the charge associated with this peak, one can able to assess the surface area of the platinum electrode. Maybe I will talk about this when we discuss electrocatalysis. Okay, so not just the electron transfer processes and adsorption, diffusion, etc. One can also assess metal deposition, nucleation, overpotential, etc. Using cyclic voltammetry. Okay, so maybe due to lack of time, I will skip few slides. But if anyone is interested, always you can post a question in the chat box, or you can ask me the question later. Okay. Now, so in the series of techniques, we discussed about potentiometry, amperometry, linear sieve voltammetry, and cyclic voltammetry. And in the case of voltammetry, the another well-popular technique is pulse voltammetry. There are different techniques which come under pulse voltammetry, like normal pulse, reverse pulse, differential pulse, square wave voltammetry, staircase voltammetry, etc. Why do we apply pulse? It is very simple. These kind of pulse techniques are very much popular in the field of sensors, biosensors, electrochemical sensors, etc. Why do I highlight these techniques in energy? Is because you can able to tune the material characteristics. Okay, let's say if you do a simple electrode deposition process, You want to prepare a size and shape controlled nanomaterial that could be used for energy conversion and energy storage application. Normally what do, you go to a hardcore wet chemical method or some template assisted method, or a hydrothermal method. You use a high temperature technique to prepare such material. But I can suggest that even electrochemical technique could also be used to prepare such kind of size and shape controlled material. How do you control the growth? You can control the growth using this pulse technique. That's the advantage of this technique. Okay. I hope you guys know what do I mean by pulse. I remember yesterday I talked about it in case of amperometry. What you do is you can apply the staircase kind of input signal, meaning you can vary the potential with respect to time, like on and off, and you can see overall we have a linear ramp, linear variation of potential with respect to time. So this is a kind of digital voltammetry waveforms. The width of the pulse is nothing but your time duration. About that time only you want to apply a pulse. Then you switch off, then go back to another potential and apply a pulse, etc. So that you can control the growth both in terms of size and in terms of shape. Okay, so that's the kind of staircase voltammetry one can apply in case of pulse voltammetry. Of course, these techniques were developed in the early 1960s. It's precisely between 50s and 60s by Sir Geoffrey Barker in UK, and later on these are modernized like square wave, differential pulse, etc. by Janet and Bob in US. Now, what is the basic behind all this pulse technique? Remember, in case of electrochemistry, it is very difficult to distinguish Faradaic and non-Faradaic process. What do I mean by Faradaic and non-Faradaic process? You guys would know. Faradaic process involves charge transfer reaction like electron transfer rate constant or charge transfer processes like proton transfer, etc. Non-Faradaic process involves no charge transfer, meaning typically the double layer formation, and there could be simple adsorption and desorption of ions. This becomes very critical in case of analyzing electron transfer rate constant. You need to distinguish between Faradaic and non-Faradaic process. How do you distinguish that? You can use a pulse method. Yesterday I mentioned, I remember, but I will correlate again. The non-Faradaic decay is very fast. Okay, so this essentially contributes to e power 1 by 6, t power 1 by 6. That's a very fast decay process, non-Faradaic process. In contrast, the Faradaic process undergoes very, very slow decay. The time constant would be t power 2 by 3 of the order of 2 by 3. So the moment you apply pulse, initially there is a fast decay, non-Faradaic, and the moment it stabilizes, kind of reaches a steady state, you can get a pure Faradaic measurement. That's why by looking at the output, you can able to distinguish both Faradaic and non-Faradaic process in electrochemistry. This is a kind of normal pulse one would apply. You can apply typically varying potential with respect to time, and you can have a rest period. That's where you give the material to grow in terms of controlling the size and shape. Okay, the typical output again in case of pulse voltammetry would be the plot between current versus potential. You would see a typical S-shaped voltammogram. Okay, so this is the current you would measure, and that current is called a limiting current or steady state current. What do I mean by that? Similar to voltammetry technique, the moment you vary the potential, there would be a change in current due to electron transfer reaction. This current value increases because of the increased concentration gradient. But the moment you reach the peak in terms of current, the process is no longer controlled by diffusion. It attains the Nernstian equilibrium, though you vary the potential. Because of the pulse technique, you would always maintain the Nernstian equilibrium, and that's why you get a typical steady state current. Okay. Now, so similarly, maybe I would skip few slides because I want to cover many things today. Let's see how far we go. Okay. So depends upon the input signal, you would get the corresponding output. See, for example, in case of differential pulse voltammetry, you can differentiate the voltage with respect to pulse. You know, as you can see, the fixed linear ramp over which you apply a pulse, and compared to this normal pulse, a differential pulse voltammetry gives you a sharp peak shaped voltammogram as an output, so that you can clearly get the peak current, maximum current, due to the electron transfer reaction. Similarly, instead of differential pulse, one can apply square wave, etc. So this is the kind of output signal you would get. In case of normal pulse voltammetry, you would see like an S-shaped voltammogram as an output. But in case of square wave or differential pulse voltammetry, you would get a typical peak-shaped voltammogram as an output. This is a much better technique where you can get a better resolution and better sensitivity, right? So these are the kind of inputs and typical output in case of pulse voltammetry. You can see normal pulse, differential pulse, square wave voltammetry, and this is a kind of similar to linear C voltammetry, etc. Staircase voltammetry. Okay, so these are of course the deduction limit, meaning that's the kind of low. If you want to look at in terms of material growth for energy conversion or storage application, you can use this pulse voltammetry technique by using a very lower concentration of the molecule. You don't have to use like millimolar or molar concentration. So that's the advantage you would get in terms of pulse voltammetry. Now, in this series, we have what is called the electrochemical impedance spectroscopy. Okay, this is the most powerful technique in electrochemistry. Just give me a minute. I hope you guys are listening to me, right? Today I'm talking too much of subject, no story. So let me continue. Okay, you guys are listening, right? You are not sleeping, I guess.
No, sir.
No, sir. Listening. Okay.
We are listening, sir.
Okay, good. Yeah. So, among the many different electrochemical techniques, electrochemical impedance spectroscopy is the most powerful technique in electrochemistry. Why do we call this as a spectroscopy? Is because there are many controversial arguments for this, but keep it in mind that, for example, in case of spectroscopy like IR, UV vis, NMR, etc., you observe a peak formation and correlate directly to the functional group present in the molecule, directly to structure of the molecule. So similarly, the output in impedance spectroscopy could be directly correlate with the structure of the electrode-electrolyte interface, which is very critical. You can pinpoint some of the elements like resistor, capacitor, inductor, Warburg impedance, etc., so that you can directly correlate the structure of electrode-electrolyte interface. So that's why electrochemical impedance spectroscopy is a very powerful technique. Maybe I will spend definitely about 10 minutes because this is very critical. Now, what's the basic principle behind this technique? This comes under AC technique. In this technique, what you do is you fix the DC potential. Okay, you fix the DC potential. That DC potential could be your open circuit potential, E0 or E half or equilibrium potential. You get me? It could be open circuit potential, it could be E half, it could be equilibrium potential, or it could be E0. All these things have meaning. Hopefully you guys would understand that, right? So you fix the DC potential over which you superimpose a sine wave of peak to peak. Okay, that's the amplitude of the signal, over which you superimpose a sine wave of peak to peak difference roughly about 5 to 10 millivolt. Okay, only in the case of corrosion you observe a large perturbation of 50 to 100 millivolt. Otherwise, you need to apply only about 5 to 10 millivolt. Why we need to apply such a minimal perturbation is because you can directly correlate the system to equilibrium. Okay, because at equilibrium the system exhibits its real characteristic. That's why you apply a very minimal perturbation. So you apply a sine wave of very minimal perturbation. That's the kind of input perturbation, potential versus time. And since you apply a AC sine wave, the output will also be of sine wave. Okay, it's like this. And you look at the output signal in terms of change in amplitude, meaning peak height, change in amplitude, or the change in phase shift. That could be directly correlated with the impedance. Since you apply a AC perturbation signal, the resistant in this case is called impedance, and the impedance has both real and imaginary part, Z prime and Z double prime. The change in amplitude is directly correlated with the real part of the impedance, okay, and the change in phase shift is correlated with the imaginary part of the impedance. And in terms of electrical circuit element, the real part of the impedance is directly correlated with the resistance alone, and the imaginary part of the impedance is correlated with the capacitance and the resistance and capacitance combinations. I will get back to this point. Okay, just to remember this, the peak to peak amplitude change is directly correlated with the real part of the impedance, and the change in phase shift is correlated with the imaginary part of the impedance. Now, since you apply again the AC perturbation signal, there is a time constant associated with this process. You can change the frequency. What do I mean by frequency? Frequency is 1 over hertz. Okay, it is inversely proportional to time constant. Normally, in case of impedance spectroscopy, you can vary the frequency from megahertz to microhertz. Now, we do have instruments through which you can vary between 7 megahertz to 1 microhertz. So you can imagine megahertz to microhertz, 10 power 12 orders of magnitude one can change. That's why this technique is very powerful. 10 power 12 orders of magnitude change. Okay. Now, so by changing the frequency, what do I mean by changing the frequency? When you vary between microhertz to megahertz, what you do is you apply a similar kind of sine wave. Within this half wave, you can apply one more sine wave, like one more sine wave even within that half. So that's the meaning of changing the frequency. So for each of those perturbation signal, you would get the corresponding output signal in terms of variation in current with respect to time. So if you look at such kind of output, it would be a complete chaotic, and you will not get a meaningful information by looking at the output in impedance. I hope you understand what do I mean by that, right? By changing the frequency, you are going to apply within this half signal one more sine wave, and within that half one more sine wave like this. So for each of those perturbation, you would get the corresponding output. So it would be very difficult to get a meaningful information by looking at output in impedance like this way. That's why the output in impedance spectroscopy is expressed in terms of two different plots. First one is Nyquist plot and the other one is Bode plot. Okay. So the Nyquist plot is a plot between Z real and Z imaginary. And the Bode plot, again, we do have two different category. One is a Bode frequency plot, where the total impedance is plotted against the log of frequency. And in the other kind of Bode plot, where the phase angle change is plotted against the log of frequency. Okay. So these are the typical output in impedance spectroscopy. Now, in case of Nyquist plot, okay, you go from a high frequency measurement to low frequency measurement. You start from megahertz or kilohertz to microhertz or millihertz. Okay. Suppose, let's say, you observe in case of a Nyquist plot, a small semicircle and a straight line. Okay, the formation of semicircle indicates the process is controlled by charge transfer. Okay, kinetically controlled process, and the formation of a straight line at low frequency indicate that the process is controlled by diffusion, mass transfer controlled process. Suppose if we don't see any straight line, if you see a complete semicircle in impedance, then that indicates that the process is controlled by charge transfer process, completely a kinetic controlled process. Now, remember, I used to take impedance at least 2-3 hours in class. I'm trying to squeeze that in within 5 to 10 minutes. So there would be a fast way of communication. But if you can listen to me, at least I will try to highlight the importance of this impedance spectroscopy. Now, the very first point of highest frequency of your measurement is called the solution resistance, which is RS, or uncompensated solution resistance. Okay, and if you fit that into a semicircle, the second intercept on the x-axis is RS plus RCT, meaning charge transfer resistance. What do I mean by charge transfer resistance? The resistance offered by the electrode towards any charge transfer process. Okay, the resistance offered by your electrode towards any charge transfer process is called RCT, and the difference between these 2 points will give you the value of RCT. And in the field of corrosion, they call this RCT as RP, polarization resistance, the resistance offered by the electrode towards polarization process. Okay, and the Z double prime maximum could be used to measure directly the capacitance. Z double prime maximum is equal to 1 over omega c. Omega is an angular frequency. Omega is equal to 2 pi f. F is the frequency you apply between kilohertz to millihertz, megahertz to microhertz, etc. So omega is angular frequency, 2 pi f. So by measuring the Z double prime maximum, one can directly determine the capacitance of the electrode surface. Okay, so that's why by looking at impedance spectroscopy, the output in impedance spectroscopy, one can directly correlate with the double layer structure. I'll come back to that structure. Okay, you can measure directly the uncompensated solution resistance, double layer capacitance, and the RCT. Suppose if you have a straight line at low frequency regime, that corresponds to mass transfer process. It arises because of the resistance to diffusion process. That is represented by a parameter called Warburg impedance. Warburg is W. Okay, Warburg impedance. So how do you distinguish this between a straight line for a diffusion and a capacitive behavior? In case of diffusion, the phase angle should be 45 degree and the slope of this line should be unity. That's how you distinguish between the straight line due to diffusion and capacitance. I'll come back to this point a bit later. Right now you assume that there is a small semicircle and if it is straight line, and this the kind of equivalent circuit one would fit to determine the parameter. Okay. Now, why do we do electrochemical impedance spectroscopy measurement? Okay, so this kind of spectroscopy impedance measurement arises because of the need to understand very fast electron transfer kinetics. As I mentioned, you can vary 10 power 12 orders of magnitude of change so that you can able to understand many different processes, starting from corrosion, adsorption, desorption, even material characteristic like conductivity, resistivity, etc. One can understand the kinetics behind any electron transfer reaction, catalytic reactions, and also in the field of sensors, energy storage devices, etc. It's very, very useful technique. Okay, so maybe due to lack of time, I will not go into very fundamental of this impedance spectroscopy. But if anyone is interested, I can always share these things through email or through questions later. Okay. Among the many different electrical circuit element like resistor, capacitor, etc., The resistor is frequency independent. What do I mean by that? At whatever be the frequency you change, the resistance is not get affected. Okay, so only the capacitance and the Faraday component of the impedance like RCT, Warburg impedance alone is affected by frequency. That's why the very first point of your measurement at the highest frequency, at a high frequency, okay, highest frequency of study would give you the value of Ru, R omega. When you go from high frequency to low frequency, there is a change from a charge transfer controlled process to diffusion controlled mass transfer process. And the frequency at which it switches over from a charge transfer to mass transfer is called knee frequency, knee frequency, and the corresponding time constant is called tau naught. That is very critical in case of energy storage devices, because this frequency would provide information about how fast you can deliver the stored charge at your material. Do you get me? The frequency tau naught would provide information about how fast you can deliver the stored charge at your interface. So this is the kind of impedance measurement one would get for a mixed control regime. Okay, so this is for a purely diffusion controlled process, and this is for a purely charge transfer controlled process. But in case of just the capacitance alone, what behavior you would get is you would get a typically straight line which is parallel to Z imaginary axis. The corresponding phase angle change for capacitant would be 90 degree. Okay, maybe I'll show you the example at later part. Now, why do we use two different kind of representation as an output in impedance? It's called Nyquist and Bode. Okay, in case of Nyquist plot, as you have seen a while ago, you cannot pinpoint the frequency dependence of the impedance. Okay, so what do I mean by that? You cannot measure the frequency directly from this kind of output. Rather, by looking at the Bode plot, this is a kind of phase angle change. I mentioned for a typical capacitive behavior, you would get a 90 degree over the frequency range. So by looking at this kind of plot, one can assess this is the frequency, this is the time duration, your material will exhibit a pure capacitive behavior. Do you get me? This is the time duration, this is the kind of frequency range. Your material would exhibit pure capacitive behavior because it exhibits 90 degree throughout this frequency region. On the other hand, in case of Bode frequency plot, the total impedance is measured against a log frequency. Okay, so you can able to explicitly understand the frequency dependent from Bode plot, which is not the case in Nyquist plot. That's the kind of major difference between Nyquist and Bode. Now, we do fit the impedance measurement to different circuit element. Why do we fit that to a circuit element? Because you can directly correlate the structure of the interface and you can directly measure the quantified parameter. What do I mean by that? Let's say you can directly correlate the electrode-electrolyte interface to different circuit element. For example, the moment you dip any electrode into an electrolyte, I mentioned yesterday that it forms a spontaneous double layer at interface. So it exhibits a capacity behavior, capacitance at interface. And in order to establish this double layer structure, the electrode will exhibit a resistance that is called resistance from the electrode, okay, RP, polarization resistance, etc. Apart from this, we do have resistance arises from the electrolyte component, and that's how you correlate a typical electrical circuit element to electrode-electrolyte interface. How do we understand this process? I used to tell a joke during my lecture in the class. For example, let's say your mother is cooking, okay? Just give me a minute, I'll take some water. Let's say your mother is cooking in the kitchen, okay? And you guys are sitting and watching TV aramsa in the sofa. So your mother suddenly receive a phone call. She said, Papa, why don't you go and start frying? Do you guys get up from the sofa and go and start frying your sabji immediately? You don't do that, right? Now, rather, your mother keep on shouting at you, then come to a singular and start scolding. Then you would get up and go and start frying, right? So, meaning you would exhibit resistance to function immediately, but with the constant persistence, you can get up and start going and frying. Similarly, electrode electrolyte interface would also behave a similar way. By applying potential, more and more potential, you can able to polarize the interface, and that resistance is explicitly mentioned as RP or RCT in case of electrode electrolyte interface. So that's why I'll go back a few slides. That's why you would use many different circuit element like resistor, capacitor, Warburg impedance, a constant phase element, inductor, etc. Now, in the case of semicircle, if you observe a perfect semicircle, then you can fit capacitance, okay? Then you can fit capacitance as your interfacial parameter. But if you don't get a perfect semicircle, suppose if you get a depressed semicircle, then you can fit what is called a constant phase element, okay? Q, constant phase element rather than capacitance. Now, this is a kind of typical output one would get in terms of Bode, and for a complete charge transfer resistant, this is the kind of output you would get in Nyquist. Now, okay, suppose I am, without discussing a catalysis, I am directly showing as an example for a output in impedance. Let's say you have prepared a catalyst to carry out a fuel cell reaction. Let's say a cathodic process of oxygen reduction reaction. Okay, so when you keep on cycling your catalytic material, you would see that the RCT increases from initial cycle to 300, 600, about the 900 cycle. You see that the semicircle keep on increasing, meaning RCT increasing. So that suggests that your catalytic material exhibit a higher charge transfer with respect to cycle. So it essentially loses the stability over the period of cycling. So that kind of assessment one can make, and this is the kind of capacitor what I mentioned earlier. If you develop a electrochemical double layer capacitor or super capacitor, the typical output in impedance would look like a straight line, which is a kind of parallel to imaginary axis. Okay, so this is the kind of behavior you would get for impedance. And the output in terms of Bode phase angle plot would be a typical 90-degree. Slides, and directly I will talk about catalysis. Is it okay? I remember I spent too much time, but I think that is useful for you guys. Now, maybe I will, just highlight importance of these techniques. Then I will get to catalysis maybe in the last 15 minutes or so. Okay. Now, the techniques like rotating disc electrode, rotating disc ring disc electrode, became very popular in recent time because of the importance to fuel cell reaction, mainly oxygen reduction reaction. Okay, recall the very first lecture I mentioned that diffusion is the predominant mass transfer, and that is the rate limiting step in most of the cases. How do you overcome diffusion? You can overcome the limitation of mass transfer by rotating the solution, okay, by stirring the solution, so that you can have enhanced mass transfer. And that's where these techniques become most popular. Why do we use such techniques? You can overcome the limitation due to diffusion, so that you can measure the kinetics of any electron transfer reaction very precisely. Okay, so I will skip the slide and directly talk about Cauchy-Lewis plot. This Levick equation provides a relationship between limiting current and directly with respect to rotation speed. Okay, when you rotate the speed, how the current changes, that relation is provided by this Lewis plot. A slight modification in the equation is provided by this Cauchy-Lewis plot. This is the most famous equation in case of RDE, RRDE experiment. Here, inverse of limiting current is correlated with the rotation speed. Okay. These are the typical components one would get in case of RDE. The advantage of moving from rotating disk electrode to rotating ring disk electrode is the following. Let's say, suppose you monitor oxygen reduction reaction. Okay. What are the products in oxygen reduction reaction? If it undergoes a 2 electron reduction, it provides a hydrogen peroxide as a product. And if it undergoes 4 electron reduction process, water is the product. Okay. And if it undergoes partially reduced oxygen species, rather than 2 and 4, if it undergoes 2.3, 3.2, 3.5, etc., the oxygen reduction reaction would result in a partially reduced oxygen species. And those kind of product analysis one can do at the ring electrode. Do you get me? One can do at the ring electrode. This is a kind of glassy carbon working, disk electrode and platinum ring electrode. So whatever the reaction you carry out at disk, the product you can able to get at the ring electrode. Do you get me? So you can use a bipotentiostat. You can use a bipotentiostat to control the potential of both ring and disk, so that you can carry out the reaction at the disk and analyze the product at the ring. It's a very, very useful technique. Not necessarily the oxygen reduction. One can also analyze any kind of electrochemical reaction, like enzymatic reaction. You know, for example, the glucometer which is available in the market, the enzyme glucose oxidase converts glucose to gluconic acid and hydrogen peroxide. The liberated hydrogen peroxide could be detected at the ring, so that you can bias the potential of the ring in such a way that either you can monitor the reduction or oxidation of hydrogen peroxide. You know, the critical parameter in such kind of RDE, RRDE experiment would be collection efficiency. That's what I showed in the previous slide. Collection efficiency, the capital N value. One can determine, normally they would provide with the electrode itself. It can vary between 0.2 to 0.25 value, but one can determine experimentally also by using ferroferry redox system, and by measuring the ratio of ring current with respect to disk current, one can determine the collection efficiency. That becomes a very, very critical parameter in RD and RRD experiment. Now, electrochemistry is not just about cyclic voltammetry, impedance, pulse voltammetry technique. The techniques moved on. Now we have technique like scanning electrochemical microscope, where one can image the sample substrate, especially with respect to catalysis. Whatever the property you observed is the average property of the system, the average property of your material. And the material may have catalytically active sites distributed over the surface of the catalytic material. One can image such kind of catalytically active site. Rather, we used to define that as birth of electrocatalysis. One can understand using this scanning electrochemical microscopy technique, thanks to the living legend of modern electrochemistry. He is Alan J. Bird, who is the man behind discovery of this scanning electrochemical microscope. I would again say that he is the living legend of modern electrochemistry. Okay, so he has developed this technique where one can image not necessarily the catalysis material. One can analyze sensor, one can analyze the enzyme distribution, etc. using this scanning electrochemical microscopy technique. Maybe I will just skip a few slides, but remember that one can image at the same time one can carry out reaction. That's the kind of nanoparticle distribution over the surface. Wherever you observe a high current, you are measuring the current due to electrochemical reaction. Okay. Now, how long I can talk now? Hello, can you tell me how long I can talk?
Sir, the next session is scheduled at 2:30. Maybe until to 1:15, sir, so that we can have lunch break.
Up to
1:45 or 1:50-ish.
Okay. Is it okay with the audience too? I'm okay. I can talk. Not a problem. Okay. Let's see how far we go with this.
Yes, sir.
Maybe up to 140, 145. Let's see how long we go there. Okay. Right. Now, so that's about the fundamental concepts in electrochemistry and the technique. Of course, I do work on both sensing and electrocatalytic area. Our group focuses on many different catalysis, not necessarily water splitting alone. But today I will only talk about water splitting. Okay. Now, if you look at the catalysis research, this is broadly been classified into 5 different categories. One is a biocatalyst. The second category is a homogeneous. Third, electrocatalysis, and fourth, conventional heterogeneous catalysis, and the fifth one is modern area of ultra high vacuum surface science based catalysis. Okay, so our group essentially focus on both bio as well as electrocatalysis. Maybe I will spend a minute or two in biocatalysis. What do I mean by biocatalysis? You can look at enzymatic reactions. You can create biomimic catalysis. You can mimic the function of biomolecules both in terms of structure and in terms of its function. Okay, both one can mimic even on the electrode surface. So that's the kind of biocatalysis we talk about. What do I mean by electrocatalysis? The very famous reaction would be water electrolysis. So why do we worry about water electrolysis? We can have a very big debate on this water splitting reaction. There are people even now, they suffer for water for even drinking purpose. But why do you want to split water into hydrogen and oxygen? No idea. We can have debate later. But right now, in case of electrocatalysis, we do have water electrolysis and fuel cell reactions. What do I mean by fuel cell? Mainly the oxidation, oxygen reduction reaction at cathode, and oxidation of fuels like methanol, ethanol, CO2 conversion, etc. in the anode chamber. So those reactions comprises of electrocatalytic reaction. And when you develop material to tune this reaction and to enhance this catalytic processes, those materials are called electrocatalysis. Okay, so in a way, electrocatalysis is defined as a process in which the electrocatalyst is being used. What do I mean by electrocatalyst? It is the ability of the substance or a material that could be used either as an electrode surface, or you can modify the electrode surface with that material that could be used to accelerate the given electrochemical reaction or given electrochemical process. For example, we can use platinum as an electrode to carry out methanol oxidation reaction. So here methanol is a fuel. When it undergoes oxidation, remember in a fuel cell reaction, oxidation occurs at anode, reduction occurs at cathode. So the methanol oxidation occurs at anode reaction. So we can use material like platinum, carbon, or any kind of modified material that can accelerate methanol oxidation process. Okay. So So this is where I was talking about. We can have even enzymes that can mimic such kind of oxidation process as well. Now, in case of water electrolysis, there are three famous reactions as far as electrochemistry is concerned. In fact, it is an advantage as well as a disadvantage for electrochemical studies. Suppose if you use water as an electrolyte, your potential window of the potential window of study is limited, because the moment you scan the potential in the positive direction, water splits. Water undergoes oxidation to give you oxygen. So the oxygen evolution reaction is a limiting step when you use water as an solvent or water as an electrolyte. And when you scan the potential in the reverse direction, initially there would be oxygen reduction reaction, okay? And when you keep on scanning the potential further in the negative direction, you would end up in a regime where hydrogen evolution reaction occur. So hydrogen evolution reaction, oxygen evolution reaction, and oxygen reduction reaction are the limiting factors, and that will decide the potential window of your study. But in case of electrocatalytic process, this becomes very, very useful. So why do we worry about this water splitting reaction? Yesterday I mentioned that thermodynamically, maybe I do have the slide, I think, yeah. Thermodynamically, water splitting reaction is not an allowed process. Probably whomever studied thermodynamics would know. It is not an allowed process. Delta G is positive. It is roughly about 237 kilocalories per mole. I can show the calculation a bit later. Delta G for water splitting reaction is 237 kilocalories per mole. But when you apply a potential, delta G is minus NFE. So when you apply a potential, you can tune delta G from a positive to negative, meaning non-spontaneous to spontaneous reaction, so that you can split water into hydrogen and oxygen. Hydrogen and oxygen both could be used as a fuel. That's the advantage of water splitting reaction, okay? That's why nowadays people talk of using water as a fuel to drive vehicle, right? By applying 1.23 volt, you can split water into hydrogen and oxygen. Hydrogen will evolve at cathode and oxygen would evolve at anode chamber. Now these are this is what I was talking about, the EMF series yesterday. You can decide upon, depends upon the potential value, you can decide which one could be used as an anode and which one could be used as a cathode. For that, the thermodynamic potential value of water splitting becomes very, very useful. Okay, so this is what I was talking about, right? When you go in the positive regime, at 1.23 volt, water split, oxygen evolves, which undergoes typically a 4-electron process, evolves. And the moment you reverse the scan direction, initially oxygen reduction happens, where the oxygen gains that 4-electron, undergoes reduction to give you water as a product. And when you keep on going in the negative direction further, water splits into hydrogen. So hydrogen evolution occur. Okay, hydrogen evolution occur. When you do a cyclic voltammetry, you would observe that when you go beyond about -1 volt or so, you see a very large current. And sometimes at the counter electrode, you would see bubble formation. You know, I'm sure whomever, doing PhD in the field of electrochemistry, you would not reveal these things to your guide. I know. Suppose without knowing, you apply a very high positive or negative potential, suddenly there would be a bubble formation in the counter electrode, and you would see that something you did mistake. It is not a mistake. It is that we do not understand the process. Okay, the bubble would occur at a counter electrode. That is because you apply a very large over potential that solvent itself undergoes a splitting reaction to give you hydrogen. That's the kind of observation you would make. Okay. Now, what is the advantage of using catalyst? Let's say in case of oxygen reduction reaction, if you do not use any catalyst, the oxygen reduction would occur at a large overpotential. But the moment you introduce any kind of catalyst, you can gain the overpotential, meaning reduction would occur at a very positive potential. You gain an overpotential, and it can also provide a stable, steady state current. So you can shift the overpotential as well as you can maximize the reduction reaction. These are the two parameters one can look for in the development of catalyst. Now, you can critically evaluate the catalyst using these three different parameters. The first one is activity, the next one is stability, and the third one is selectivity. All these things become a very, very critical. This is where you play around with the material in terms of adjusting the potential. Okay, suppose if the water splitting occurs at an over potential of 600 millivolt, you want to play with the activity so that you can reduce the over potential. That's the first point. And the second point, not just the activity alone, your catalyst should be stable enough, meaning the prolonged water splitting should give you oxygen evolution or hydrogen evolution for a longer duration of time. That's about stability, and it should be selective. Okay, suppose if you have a water and alcohol mixture, your catalyst should be selective to water splitting reaction alone. It need not split alcohol into a lower carbon fraction products. Okay, so these are the three parameters. Of course, one can play with these things to maximize the electrocatalytic reaction. And electrochemically, you can evaluate and understand the mechanism behind such processes using Tafel slope. Yesterday I talked about this. From Butler-Olmeri equation, one can approximate and get the Tafel slope. And to monitor this oxygen reduction reaction, we can use this RRD experiment so that you can able to assess the product. Now, research-wise, maybe I should spend 1 minute at least on this slide. Okay, research-wise, always you would like to quantify your parameters. You would like to quantify your catalytic activity by correlating with either the geometric area or the surface area or the electrochemically active area. Okay, so the geometric area is a kind of very straightforward measurement. You can measure the geometric area of your catalyst. This surface area normally you would correlate with the BET measurement, right? Brunner, Emmett, and Teller surface area isotherm based measurement, but that may not reflect the real active surface area of your electrochemical reaction. So for electrochemical reactions, you need to always correlate your catalytic parameter with electrochemically active surface area. How do you measure such electrochemically active surface area? You can either use such kind of peak in cyclic voltammetry so that you can directly integrate the peak, measure the charge. What I showed in the during discussion of cyclic voltammetry, you can measure the charge under this peak, and you can able to measure the electrochemically active surface area. The closest parameter one can use to determine the activity of the catalyst is turnover frequency. Okay, there are formulas one can use to determine this turnover frequency. Okay, so this is what I was talking about, the thermodynamics behind water splitting reaction. So OER, the potential is roughly about 1.23 volt, and for HER, which occurs at 0 volt. So overall, this is the value you would get for a water splitting reaction, and delta G value one can determine is about 237 kilojoules per mole. Okay, I'll skip some of the basic fundamentals. So this is where from Butler-Ulmer expression, one can get the linearized regime, very small linear relationship between current and potential. You would end up with a Tafel slope. Tafel equation, which is eta is equal to A plus B log I. Nowadays, people use this Tafel slope as a criteria to assess the catalytic material for many different applications like OER, HER, and ORR. But please remember, this Staffel slope values have been derived to understand the mechanism behind hydrogen evolution reaction. Classically, they derived this Staffel slope relation. They made a Staffel measurement to understand the mechanism behind electrochemical reaction. It do not describe about catalytic activity. Please understand. Okay. Now, what are the mechanisms? One can get Walmer. Maybe I'm not sure whether I have. Yes, one can understand Walmer mechanism, where adsorption of hydrogen is a rate limiting step, or we have Walmer-Hierowski mechanism, where the interaction between adsorbed hydrogen atom would be the rate limiting step, etc. Okay, so such kind of mechanistic information one would get from this Staffel slope measurement. But I do see a lot of reports now. They say that if you have a Staffel slope less value, it's a good catalytic material. It's not so. Anyway, we can argue about this. That can take a lot of time. But right now, I want to cover some of the basic concepts. Now, whenever you talk of any electrocatalysis process, the Volcano plot becomes very, very critical. This is a plot between current density versus the bond strength between the adsorbate and adsorbent, the hydrogen adsorption to metal, for example. And this provides information about the compromise you need to make between adsorption and desorption. Okay. Platinum is a well-known electrocatalyst because it displays a very high current density for an electrocatalytic process with very low strength, kilocalories per mole, meaning it requires very less amount of energy and gives a higher amount of catalytic activity. The next best we have is rhodium and iridium and rhenium. So as you can see, many researchers are involved in developing cost-effective material because these materials are high cost, and that's where they come up with the transition element based catalytic material, and these are the worst catalyst one would get in terms of indium, tantalum, cadmium, lead, etc. Okay, so this is the kind of Volcano plot which becomes very, very critical, and these Volcano plot have been derived initially for hydrogen evolution reaction, and later on now people are working for such kind of Volcano plot for oxygen evolution and oxygen reduction as well. Now, maybe one critical parameter in terms of catalytic development I want to discuss. Always, what do we do is we prepare a material and we disperse the material in a solvent and drop cast on the electrode surface to study what is the role of this catalytic for ORR, OER, or HER, etc. Now, you need to basically find out the optimum thickness of your coating, so which is a very critical parameter. You need to do this through trial and error method. How thick your coating could be, because if your coating is thicker, then it can lead to large capacitance rather than the electrocatalytic activity. Okay, and of course many different parameter like conductivity, accessibility of the area, etc. matters. In case of homogeneous catalysts, okay, the thickness of the film also matters. So that's what it talks about. Now, maybe I will describe about only one work and I will wind up my talk. Okay. So though we developed many different catalytic material for this reaction, I would like to highlight a very, very simple method, right? You do an electrolysis, you use an anode and cathode, you do a water electrolysis. What we did here is we used a titanium substrate as an anode and platinum as a cathode. And when you anodize this titanium, by playing with the composition of the electrolyte and the current density, one can tune the resultant output, as you can see, a beautiful honeycomb-like structure of TiO2 nanotubes. You can control the growth of this nanotube. You can see beautiful ripples. Okay, so all these things arises because of the variation in current density distribution. You can see the porosity. Some tubes are very single. Some tubes are merged 2 and 3 tubes together. All these things could be understood through fundamental understanding of how the current density distributed during the anodization process. And also one can control the growth in terms of length and diameter, porosity of the tubes, etc. So that this could be used directly to water splitting reaction. This is just electrocatalytic I am talking about. Since it is a titanium based material, one can also look at photoelectrochemical concept. One of my colleagues, Dr. Satish, will talk about this maybe tomorrow, the photoelectrocatalytic effect, right? So the moment you shine a sunlight onto this material, you can tune the band gap so that you can matches with the energy level of the water splitting reaction. Okay, so that's about photocatalytic. Rather than photocatalytic, even by applying the voltage itself, you can play around by tuning the band gap simply by applying a potential. So you can see that the oxygen evolution is enhanced by about 40-fold, and similarly by hydrogen evolution is enhanced about 100-fold compared to the normal catalysis. Okay. Similarly, we also prepared graphene quantum dots where you can introduce nitrogen doping into this graphene quantum dot, and you can couple with the transition elements like cobalt. Why I showed this work is, remember I mentioned that transition materials are a kind of lethargic catalysis mainly for hydrogen evolution and oxygen evolution reaction. But by preparing a composite with highly conductive, and you can tune the band gap through nitrogen doping, one can get materials like beautiful flakes, and you can use that for both OER and oxygen reduction reaction. So such kind of processes one can observe, and you can able to analyze that with both cyclic voltammetry experiment and through RDE and RRDE experiments. Okay. So maybe finally to conclude, tuning electron transfer reaction is very, very critical. And by tuning such kind of electron transfer reaction, you can modulate the catalytic behavior, and I can extrapolate the same concept to sensing behavior as well. Okay. Ultimately, to lead a life with smart materials and smart sensing, right? You want comfort in our life, right? What do I mean by smart material and smart sensing? Let's say, you guys are sitting in your sofa or chair in your house and listening to me, and you are listening from the morning, what this guy Ganesh is talking about. Always current to potential, electrochemistry, capacitance, resistor, etc. Then you get bored of my talk. You simply okay, I will conclude. Yeah, you would get bored of my talk, and simply you lean on your chair. Okay, then the chair understands that you are not interested, so it is being converted into sofa so that you can sleep aramse. You can sleep comfortably. That's the kind of smart material we talk about. But remember, on the other hand, the chair can also prick meaning kundu seyochi kutra madri. Okay, it can prick you and say that, see, this guy is spending like almost 2 hours talking about the importance of electrochemistry. How do you understand the basic concept? How do you use this technique to evaluate your catalytic material, etc., so that it can prick you? Then you listen to me because it may be useful for your career, etc. And remember, nowadays research is not a single disciplinary. Though you may be a physicist or a chemist or a biologist, but if you could take concepts from other field, it becomes completely multidisciplinary, and it can provide useful information so that you can solve and provide solutions to the global issues, what I highlighted in the earlier part of my lecture. So essentially, you need multidisciplinary group effort. So finally, thank you all for your patience listening. And I would be happy to answer any queries or question you may have. I would also like to thank finally, of course, Dr. Punduandian sir for providing me an opportunity to share with you guys whatever the knowledge I have in the field of electrochemistry and electrocatalysis. So thank you very much. I'd be happy to answer any queries you have.
Thank you, sir. Thank you for your wonderful lecture. Maybe there are some questions already there in the chat box.
Okay, I'll come out of my presentation so that
please,
okay, so that I can directly. All right. Oh my God, already 63 chats are there. My okay.
Not much question. Only they are appreciating you. That's all.
Comment so okay. If you have any questions, you can also ask me directly if you want. I'm seeing
one question from Divya. Senthil Kumar. Is there any advantage of using 2-electrode system compared to 3-electrode system?
Yes, very good. Yeah, that's also a good question. Yeah. Now, in order to do electrochemical reaction, you don't need always 3 electrodes. We can also carry out electrochemical reaction using 2-electrode system. But if you want to measure quantitatively some of the kinetic parameters like electron transfer rate constant, charge transfer reactions, etc., we do need a 3-electrode system, because yesterday I talked about using a bigger area counter electrode. So that's why you need a 3-electrode system. But for a process like electrode deposition or water electrolysis, etc., it is sufficient enough to use 2 electrode. Okay. In case of such arrangement, let's say if you want to do anodization process, you connect the working electrode to anode, and you can short circuit reference and counter electrode to the cathode. So that's why you can move. That's where you can move from 2-electrode to 3-electrode systems. I hope that answers your question.
Yeah. One more question: whether it's possible to combine both biocatalysis and electrocatalysis for the catalytic activity?
Yes, beautiful. Yes. Let's say, for example, I want to monitor an enzymatic reaction in case of biocatalysis. Okay. The enzyme will have its own E-half or E-net value. So, suppose if you apply a potential along with that E-half value of the enzyme, you can maximize, you can accelerate the enzymatic reaction. So you can maximize the activity. So always the coupled system of potential like electrocatalysis and biocatalysis, rather you can say bioelectrochemical catalysis, would provide an accelerated catalytic reaction, so that you can tune the electron transfer reaction. Rather, you would get a higher catalytic activity. Yes, combining both will give you better catalytic activity.
Okay, one more question is the stability of biocatalyst over heterogeneous catalyst.
Yes, good question. Yeah. So when I say this again, bioelectrochemical catalysis, biocatalysts are known to be highly unstable, because it depends on the temperature, it depends on the pH. The biomolecules would become inactive, and maybe the turnover frequency is very less. Over the period of time, the biomolecules undergo fouling, so the stability is rather poor in case of biomolecule. But when you combine with the electrocatalysis, you can enhance the stability by applying the potential, so that you can retain the activity of such biocatalysis. I can see you are also talking about heterogeneous catalysis. Yes, heterogeneous catalysts are always those catalysts always exhibit a high stability over biocatalysis. Okay.
Okay, one more small question is, can you spell the plot name of ORR water splitting reaction?
Say again, sir.
spell the plot name for ORR or water splitting reaction?
Uh, sorry, sir. Plot
Uh,
means.
she
Sorry.
she's meaning that the Tefel slope. That I think that she's meaning. I don't know.
Okay, okay. So what is the? I mean, how do you plot ORR and HER? If I am right,
I
that's the
think so.
question.
I think so.
No, sir. Actually,
The plot name. What
Yeah,
is
I
the
hello.
think. Yeah, please ask.
Yes, sir. You said some volcano or some name, no? For platinum is having higher catalytic activity. The spelling of the plot name.
Yeah, that is Volcano. Volcano. Volcano plot. I can type in the chat box if you want. Uh, this is the Volcano plot. This is nothing but the plot between current density versus the bond strength between adsorbent and adsorbate. For example, if you are monitoring a hydrogen evolution reaction, you want the metal to adsorb hydrogen at the same time. In order to evolve, in order to release hydrogen, it has to have a desorption also parallelly. So you need to make a compromise in the adsorption strength in terms of energy. So that's where the plot becomes very critical. You need to have a higher current density, at the same time lower metal hydrogen adsorption bond strength. That's where this plot becomes very, very critical. So this plot is Volcano plot. Remember, you can also refer a book called Bakris and Reddy, Modern Electrochemistry, Volume 2A and 2B by Bakris and Reddy. That book talks about this plot very well. But remember, this plot has been generated for hydrogen evolution reaction. Fundamentally, this is for hydrogen evolution reaction. But people have started adopting that concept to oxygen reduction, oxygen evolution reaction, etc. And there is a recent review paper that provides information about OER Volcano plot, which is very good. Okay, you can refer literature.
Two more small questions. That's all. Why CV, GCD, and EAS studies are highly concentrated for energy storage devices? Why not DPV?
Oh, good. Okay. Now, in case of energy storage and energy conversion applications, always you look for catalytic material. For example, suppose you prepare a material, okay, and you want to know how much energy can be stored in the material. So you want to measure capacitance, or in terms of battery, it is capacity. Okay, or voltage, what's the voltage range one can have? That's the kind of parameter you measure. Now, the techniques like cyclic voltammetry or charge discharge, impedance spectroscopy, etc., would provide a direct measurement of these values. On the other hand, differential pulse voltammetry could be used only to maximize the signal to noise ratio. In fact, those kind of pulse techniques are very well and widely used in sensor field, because in the case of sensor, you want to maximize the sensing signal and reduce the noise as lower as possible. Now, I highlighted during my talk that you can prepare the material. Let's say you can control the growth of your material in terms of size and shape using this pulse techniques, so that when you use such kind of DPV, you can control the growth. You want to grow only for a shorter time in the beginning, and next when you apply a pulse, the growth would be in a completely different direction and in different dimensions. So these kind of techniques are not widely used to analyze, or rather to answer your question straightforward, DPV is not used to analyze energy storage or conversion material, but it could be used to prepare such material. I hope that answers your question. Yeah.
Okay.
Yeah.
There is another question. What's the latest state in water splitting?
Very good. The latest state is people are still searching for an alternative viable material to efficiently get a higher amount of hydrogen and oxygen. Now, if you ask my personal opinion, I do not worry about the quantity of water and oxygen produced now. Suppose I would use this as a platform to discuss what happened maybe on October 3rd. Probably you guys would have heard about this Vaibhav summit. Our Honorable Prime Minister has inaugurated on October 2nd during Gandhi Jayanti's, he inaugurated Vaibhav summit. There, we have provided, Government of India have taken an initiative to create a platform between discussion of NRI researchers with Indian researchers. CECRI was one of the champion institutes in energy. I was involved in, I was also one of the coordinator in conducting that event on sustainable mobility technology, okay, where we discussed about fuel cells, batteries, supercapacitor for e-mobility application. So what we discussed is, it is not about, in terms of just hydrogen, in terms of just water splitting reaction alone, I will discuss now. It is not about splitting water into hydrogen and oxygen alone. How do you store this hydrogen and oxygen to utilize as a fuel for e-mobility? Okay. As a student, if you ask me, you can use even a platinum electrode. Platinum will do all these three reactions, like oxygen evolution if you go in a positive regime, oxygen reduction if you go in a negative, and if you go even further negative potential, it would also liberate hydrogen. Okay, so just to play with the cost, we find an alternative material like carbon based or transition metal based material for these reactions. The latest invention in the field of water splitting is still searching for a material. I would rather personally say that, in my opinion, we need materials which can not only evolve hydrogen, but at the same time it can store, so that we can utilize that for e-mobility applications. I hope I am also talking.
Already too late. It is 1:45.
At least you guys are sitting. Yeah.
Maybe let's thank Dr. Ganesh for his wonderful lecture on very basic starting. He has started from very basic fundamental from the electrochemistry. Now he has touched upon the water splitting. I hope all the participants enjoyed his lecture for yesterday and today. I hope that some of the participants may start their own research in this field. Okay, with that much he has explained the basic to the current application. So you all enjoyed the lecture by Dr. Ganesh. I thank Dr. Ganesh for his effort to deliver a lecture yesterday and today. It's around, today he has talked about more than 2 hours in this lecture. Okay. So I thank Dr. Ganesh for his wonderful lecture. I also thank all the participants for their patience, because they have stayed till now. Its time is almost 2 o'clock. Again, Dr. Ibrahim Ganesh is also joined. I think he's from ARCI.
Yeah.
Sir, yes, sir. Tomorrow I will be presenting, sir.
Yeah, okay, sir. Thank you,
okay,
sir.
Sir. Thank you, sir. Thank you, sir.
Okay. Tomorrow he is going to deliver a lecture, another lecture in the morning. And maybe we conclude this session with this one. And again, we start the next session at 2:30 by Dr. P. Raghupati from CECRI about the batteries. Okay. Maybe we can stop it here. We can leave it right now, and we can join again.
Okay, sir. So thank you for the opportunity. Take care.
Thank you, sir. Thank you so much. Thank you, sir. Ibrahim, sir. We will see you tomorrow, sir.
Yes.
Thank you, sir. Thank you.
If you would like to join in the afternoon session also, please welcome, sir.
Sure, sir. Sure. I will see the timing and I will join. Sure.
Okay. Sir Ganesh, sir, also please. This Ibrahim Ganesh.
Sir.
You also please join in the afternoon session.
Yeah, sure, sir.
Okay, sir. Thank you. Thank you.
Thank you, sir.
Thank you.